Hello and welcome to this clip going through question 3 from the 2006 Chemistry Olympiad paper. This is a particularly nice question for second year students because it goes through or follows quite closely much of the syllabus from several A-level exam boards when we're looking at things like carboxylic acids and esters and further derivatives of these compounds. So as usual with all Chemistry Olympiad questions, there's a bit of background just to give the chemistry that's being tested a little bit of context. So it talks about acyl chlorides and gives them a general sort of formula of RCOCl. And these are highly reactive compounds which rapidly react with water to give carboxylic acids, and they react with alcohols to give esters. So in the acyl chloride group, you find a delta positive carbon that's actually more partially positive than you'd normally expect because you have two very electronegative atoms attached to it. So this gives us two polar bonds which are both susceptible to nucleophilic attack. So part A starts us off with something quite accessible, a balanced equation. So you need the reaction between ethanoyl chloride. So if you look at the general model of an acyl chloride, you can see that the ethanoyl chloride will have two carbons in it, so R will be a methyl group. So that gives us CH3COCl, note the two carbons, therefore ethanoyl chloride, plus H2O giving us CH3COOH, so our two carbon chain is maintained, and every nucleophilic reaction with an acyl chloride will involve the chlorine coming off. So that particular bond, CCl, is very susceptible to attack. So the next question, which is the balanced equation for the reaction of propanoyl chloride with ethanol, you're still making HCl, but this time the organic product's slightly different. You've got an ester that's made instead. So that means that the ethanol must be behaving as a nucleophile. So now we've opened the question with a couple of straightforward examples that are pretty similar to what you find in an A-level textbook. It now starts to get a little bit more applied. So it talks about phosgene, which is carbonyl chloride or COCl2. It actually used to be used as a gas in the First World War, and it's very toxic, and it was developed initially a long time ago to carry out some horrific attacks on some of the soldiers in trenches. So a slightly more modern peacetime use for it is explained here. So it's essentially a diacyl chloride. So if you imagine you've got a carbonyl, C double bond O, but two chlorines coming off the carbon. So it's a bit like the ethanoyl chloride we looked at earlier, except no R group, there's another chlorine. So it reacts similarly with alcohols. So because we've just done a question on alcohols, part B, we can take that idea and apply it a bit more here. So it asks you to draw the structure for compound A. So if we look at the OH group that's present in the first compound there, you can see that it's got an oxygen, and that oxygen will obviously have a lone pair. I think what they're talking about is the idea of that acting as a possible nucleophile. So in other words, what happens is H plus is released from the starting compound's OH group, and it's replaced by COCl, which is the carbonyl chloride, or the remnant of the carbonyl chloride. So the second chlorine atom that was in COCl2, you'll notice that's not here, that's actually formed HCl as the H plus is released. So you always make HCl when you react an acyl chloride with a nucleophile. So it asks you to draw the structures in part D of phosphoryl chloride and thionyl chloride, and clearly indicating their shapes. So we're using VSEPR theory, which is straight out of first year A-level. Then they also want the oxidation states of the phosphorus and the sulfur in these compounds. That also requires a little bit of thinking back to first year as well. So obviously remembering that double bonds represent a single bonded pair, even though technically it's actually two bond pairs, in VSA-PR theory, we consider them, for the purposes of repulsion, as a single bonded pair. So obviously the phosphoryl chloride is tetrahedral and the thionyl chloride is pyramidal or pyramidal. So what you've got to look at for the oxidation number is the number of bonds that the central atom involves in bonding. Sorry, the number of electrons, I should say, that the central atom involves in bonding. So I'm saying central atom in this case because it is the central atom they want us to talk about. They want us to talk about phosphorus and sulfur. So using this information, we can deduce what the oxidation number of the phosphorus and the sulfur atoms are. So being more electronegative than either phosphorus or sulfur, the oxygen and the chlorine will both assume a negative oxidation state. So therefore we're left giving the phosphorus and the sulfur positive oxidation states. So that means that phosphorus is +5 and sulfur in thionyl chloride is +4. So in part E, they want us to write an equation for the reaction between thionyl chloride and water. So if we look at the contextual information at the top, in the second paragraph, right next to where on the graphic it says phosgene, they're talking about other oxyl chlorides containing bonds to chlorine and double bonds to oxygen, such as phosphoryl chloride and thionyl chloride, react in an analogous fashion. So therefore, what that means is obviously anything that we've already worked out in the sense of what an acyl chloride does, you can apply the same to thionyl chloride. So one possibility is the simple reaction that makes sulfur dioxide and 2 moles of HCl. So the other option is the formation of sulfuric 4 acid. Both of them would work, both of them are perfectly acceptable in this case. So let's now go on to the next part. So part F wants us to do a phosphate ester. Now you won't have come across a phosphate ester before. You may have come across normal organic esters where you have a carbon double bond oxygen and also a carbon single bond oxygen, both of them attached to the same carbon. That's the basis around which an ester is built. So a phosphate ester will be along similar lines. But don't forget, a phosphorus can have more bonds than a carbon, but it's in group 5 instead of group 4. So we've got to take this into account when we're thinking about what it might look like. Okay, so you've got two possible structures here you need to think about. So they want the structure with 1 mole and the structure with 2 moles. So remembering that every time you get a nucleophilic attack onto the carbon in carbonyl chloride or in an acyl chloride, think of the carbon this time as a phosphorus. So you get an HCl coming off, that means PCl bonds are what's being attacked. So hopefully you can see both structures, including the one that I've tried to squash in at the bottom of the screen, so apologies for that slightly untidy layout. But by adding how many HCl's come off, you can see quite easily what's actually going on. The methanol comes on as a nucleophile and attacks the PCl bond, or attacks the phosphorus itself, beg your pardon, and the PCl bond breaks. So now we're into the final part of the question, and as you can probably see, it's more of a calculation type. So I'm going to clear a bit of space to allow us to do that. So, moving on to the next question. It's a calculation one, and what I've done is I've taken the information in the question and I've turned it into equations. So the first equation, obviously you've got to do something with the chlorides, which I'll come back to in a second. The second equation is simply H3PO4 plus PlCl3, giving you an acid called B. And B reacts with silver nitrate to make a white precipitate, which contains 71.3% silver, 10.2% phosphorus, and 18.5% oxygen. So although it might be tempting to consider that the white precipitate could be silver chloride, the problem with that is that silver chloride doesn't contain any oxygen. So you've got to be careful not to fall into a trap here. Now, like I said earlier, the POCl3, whenever it reacts with something in a nucleophilic manner, you tend to get HCl given off. So obviously there'll be 3 HCl's coming off as well as the H3PO4, which I'll just pop those in a second. So what we've got to do is to think about the likely formula of that white precipitate. So we now have the number of grams of each of those elements. So that allows us to get the number of moles of silver, phosphorus and oxygen. So we can now work out the empirical formula of our precipitate. I'm not saying that is the formula of it, but that's the empirical formula, which gives a phosphorus to oxygen ratio of approximately 1 to 3. So that must mean that the phosphorus-oxygen ratio in acid B must be approximately 1 to 3. So if we start picking up the clues, the phosphate ion in H3PO4 is that structure. So reacting the H3PO4 with POCl3 adds on another phosphorus and oxygen. Maybe you get 3 HCl's made at the same time to get rid of the Cl3. Because if there was chloride within B, then the white precipitate would have been silver chloride. But it wasn't, it was silver with phosphorus and oxygen. So now, if we think about what we're left with, we've got 2 phosphorus, we've got 1, 2, 3, 4 oxygens, we've also got an extra oxygen. Let's have a think about what we could do with this. So we aren't informed that B and AgNO3 actually react in a 1-to-1 ratio. It doesn't actually tell us that, so we can't really assume that. So I'm going to propose that structure there as my acid B. So it just says suggest a structure. I'm not saying that is the structure, but working on what we've got as clues, that seems to fit the bill so far. Then they want an equation for its formation from phosphoric acid and POCl3, and then telling you that the only other product is HCl. So they have now told us that HCl is made. So starting with our reactants and products, we need to think about how many HCl's we produce. So starting with the number of chlorines we've got, we definitely have 3 HCl's. So now we've got to think about the hydrogen and the phosphorus. So there must be at least 5 moles of H3PO4, because we want to lose 3 hydrogens as HCl to cater for the chlorine, and then 3 times the moles of B will allow phosphorus to be balanced on both sides to take into account the phosphorus we've also got in POCl3. So rather than going through each individual stage of that, maybe you might wish to pause the clip and have a work through it yourself so that you're happy with how it was derived. So if you're a second year student, there's obviously quite a lot of stuff here you can draw from. If you're a first year student, maybe not quite so much, so because there's some second year chemistry in here, but there's definitely some first year stuff in there like shapes, deriving equations, applying that kind of stuff, and the calculation at the bottom. Although tough, it's actually possible to do using ratios and just keeping a sort of cool head about it as you go. So until next time, thanks a lot, and hopefully this clip has been useful, and maybe even inspired you to give the Chemistry Olympiad a go this year. So until we meet again, see you soon, and thank you for your time.